please open your notes, right? I'll be going to another screen, so if you want to stop me, please really give me a shout. I cannot see the hand and so on. Okay, so just interrupt. All right. Now, if we go to that, notes now, okay. So the first one, you see, the problem till far is that we do not have any way to assert whether our so we are saying many things. For instance, in the last exercise, 2.3.1, we have seen several things, right? It is essentially one thing I must say over there. I think I said it last time, is this union thing. So union of x is precisely those y's such that there exists a z in x and y is a member of z, right? And then you see over here, once you say this, so as I said, the picture is like this, that as if your x is a collection of these things. So these are the sets inside. So, and then you take things over here and put them inside over here. That's your union. So essentially, this possibly you could have seen earlier as an indexed union. So possibly the other familiar notation with you is something like this. Remember, this was obviously x, let me say y, such that there exists an I in I with y in ai. Now the problem, the connection over here is the intermediate step, which is making of this set. This is our x over here. Oh, I'm not winning. That is Eric's reply. Okay, so this is our x, and that's, so we have directly spoken about the indexed union instead of while in our naive approach or previous approach, possibly you first define x union y, and then you define the index union. So this is the alternative. Remember, there was also this one defined. This is y, which says that whenever z belongs to x, this implies that y belongs to z. Okay. So this statement is alternatively also sometimes written as for all z. For all z belongs to x, y belongs to z. And you will often see that I am replacing this kind of a, this is called the universal quantifier, I am replacing by this implication statement. Yeah, and that is exactly what happens. So that is the replacement that we are going to do quite often. So this was about this union and such things. Now coming back to today's material, the whole point is I'm really trying to push it down to make this. So you see, we have not even. So firstly, so the existence of a small set. We don't know till yet. So it is not quite apparent that there will exist a small set. And one, you see, you must immediately realize this theorem. The following two statements are equivalent. What are they? There exists a small set and B, this is a small set. So let me write as I am writing. So empty set is a small set. Why? Well, the proof is very simple. Obviously, the proof is very simple. Obviously, B implies A is trivial. This is trivial. We have already assumed that the empty set is a small set, so you know there exists a small set. So from A implies B, assume X is a small set. So you know that there exists a small set. Now, by the axiom of power set, there exists a Y such that Y is small and Z is a subset of X implies that Z is a member of Y. Right? So in particular, since empty set is a subset of X, we have proved this already. I think it was one of the first, it was equation 13. Yeah? Since empty set is a subset of X, empty set belongs to Y. So empty set is a subset of X, empty set, which implies that the empty set is a small set. Right? So that is the proof. So you see, the existence of a small set is the same thing as saying the empty set is a small set. And the empty set is a small set is not even. But if you look into 3.1.1, it just says that if you have a small set X, so it's an implication statement. I want to pin it down. There might not exist any small set. So small xy, look into equation 49. Small xy, the hypothesis is false, but the implication statement is still true. You realize this? You realize this? Even though we have not exhibited a small set, yet these equations are true. The equation 49, 50, 51, all these implication statements are true. So implication statements one has to be very, very careful about. Yeah? So if we were in a world of sets where there were no small sets, then also if X and Y are small sets, the singleton X, the unordered pair XY, the ordered pair XY are all small sets. So you see, that's how it should be read. That I don't know. So suppose if x and y are small sets. So you are now assuming it. So you assume that x is small and y is small. That's what I mean by writing small of xy. Now, how do you say that this is small? Well, you can make this set obviously, because that is your axiom of which axiom tells you that this you can make this set. This set is exactly this set. This is a formula. When you have chosen your x and y, so x and y is fixed. So this is a formula which involves z as a free variable, and so axiom of set building tells you that there exists a small set such that this is true, right? Z is small and this statement is true. So there exists, and that small set, so the collection of that small sets is actually xy. Okay, so you can make this. All right, but remember, I want to say that this is a small set. See the difference? I can say that x is a small set, so I can, but still now I cannot prove that this set is a small set. Is it clear? There is a subtle difference. I am saying the steps again, or could you recognize the subtle difference? Let me know. Now, yeah?
So just repeat what you just said.
Okay, so let me go back to page 7 of your notes, where the axiom of set building is given. So this is axiom 2. What is it? It says that phi x is a formula in which x appears as a free variable, and it is not involving the set A. Okay, so you are saying that there exists a set A such that x belongs to A if and only if x is a small set and phi x is true. Right? See, it did not say anything about this A. The smallness criterion of A is still not said. It just says that there exists a set A with this property, and using this we said that we are going to denote this A by, so such an A, we shall write it like this, and therefore along with the axiom of extensionality we see that this denotes a unique set, so we can write this. Okay? Now, the smallness of this set A is not known till yet. So, what is the problem? Here our phi z is equal to x or z is equal to y. Since you have chosen your x and y, these are actually, once you have chosen them, they are fixed. So this is a formula in which z is the only free variable. So what is this set by our definition, or by the axiom 2? This is the set of all those z's where z is small and z is either x or y, and that we agreed to write in this way. Clear? So axiom 1 and axiom 2 tells us that such a set exists. But till yet we don't know whether this is small. Is this clear? X and Y are small, but the unordered pair XY till now is not small. Right?
Yes.
Correct? Okay.
Correct.
Okay, so now let us think. How so just axiom 1 and axiom 2 would not allow us. Welcome, Eric. We have started, but I believe you'll get the recording. So, but how do we prove this then? Well, let's try and think. Let's try and think. We want a set, right? Such that we want a set. So what is the problem? The problem is, so you have to, so to prove that this is small, which is, what do you need to show? So you need to find a set, may not be small, such that a set, say A, this unordered pair is a member of A. So if we can find this A, we are done, right? Right? Agreed?
Yes.
Yes, doctor.
Okay. Now, use your naive notion. How can you make this? How can you make this? So it's a set. So, if you have somehow, if you can put in, okay, I leave it to you. How do you think that if I give you what are the possible candidates for A? Think very naively. I have two elements. I want to make the set of those two elements X and Y, and then I want to find a set A which will contain this X and this set X and Y. What would you think? How would you go about this? So let me write it naively. What are the possible candidates? Candidates of A such that start thinking, just anything, any two X and Y. Now, how can I make a set How can I do it? Yeah?
Could you just put extra brackets around it? So make it the sets. Or is that what we're trying to prove? I'm sorry, I'm a bit.
Okay. Extra brackets means, again, I don't know whether this is small, so extra brackets means again boiling down to the same thing. Trying to find a singleton of x,
Understood.
that's the same thing, right? Again, it boils down to that.
Yeah.
So, what else? So that root, putting another bracket around it doesn't work. What else?
Okay, but how much are we given in terms of our starting point? Even if we are thinking naively, are we allowed to take unions?
Yes. Go ahead. Yes.
Consider the singleton x. Also consider the singleton y, and then take their union.
So taking this is problematic. It's again the same story, because this set is built up in. How can we build this set? This comes via here, Axiom 2. It doesn't say that this is small. So that way it doesn't work. Okay. So suppose, as you said, I have this set X. So if what happens if I take the union? Well, as we have seen, so this is X union Y. Okay? This is X union Y. Alright? That's the notation that we gave, right? A little earlier. I mean to say, in the if you see, where is it given? It is one of the exercises where I used it. Where from 24 X union Y, it's in the last exercise, 2.3.1. X union Y is union of XY, right? So I have established this notation. Now let me think. I've taken in everything. What are the subsets of X union Y? What are the subsets of X union Y? The problem is, well, I will have X is a subset of, I don't know whether this is small or not, but it tells me that if I look into the axiom of power set, it tells me that for all sets X which are small and for all there exists a set of its subsets. So that approach, but remember, I am given this. This is a small set, and I know that this is a small set. So how can I bring it? Now think, if this is a small set, then by axiom of power set, what do I get? I get from the axiom of 4, I believe, 3. It says, gives a small set say I'm writing it over here as x prime with the property that gives me a small set such that whenever z is a subset of x implies z belongs to x prime. So using Axiom 3 and Axiom for set building, I can make this set 2 to the power x as I wrote it. This is the set of all z such that z is a subset of x, right? So this is the power set of x. So when x is, I still don't know whether 2 to the power x is a small set or not, but I know that this set exists. Good. And x is a member of this set. Okay? Similarly, y is a member of this set. So now I have obtained two sets wherein I have brought in. So now think, how can I bring in this? So I have
from the notes, it's axiom 4, but then it reads that the power set that we build is a small set. So we know that 2
yes
to the power x is small. Okay.
Good. Okay, good. Yes, you're right. 2 to the power x is a small set. Good. So that's exactly axiom of power sets. So axiom 3, good, exactly tells us small x implies small 2 to the power x. Good. Now can you use the axiom 4? What does it say?
Axiom 4 is the power set axiom.
Sorry, axiom 5?
Is pairing.
Axiom 5, if you use it... sorry. This is axiom 4. Yeah. Axiom 5, what can you say similarly about this set, about the union of x when x is small? What does this say? Axiom of union. Use it in the same way. What does it say?
It says that the union of
the union is a subset of that B, right? Which is given by axiom of union, and that B is a small set, right?
Yes.
And therefore it tells us that small x implies the union is also small, right? Clear? Okay. So now we have, starting with a small set x and a small set y, we have its power sets and its union, a small set. So now can you tell me, how can I make a set a possible candidate of a set which contains this double, this unordered pair xy? Now a little more to think. give a few minutes to think.
Could you take the union of the power sets?
Union of the, okay, so let's try. Which power set?
Power set.
So roughly speaking, you're trying to think.
Well,
Try with an example, with some examples. So that's why I said we'll first work naively, and then that would give me the answer. Okay. We didn't actually then consider Axiom 3 till yet. What does it say? Look into, for all x and y, for all x and y, it says that there exists a small set A such that x is a member of A and y is a member of A. Right? So, this is a subset of the A given by the axiom of pairing. Right? So the same logic tells us, therefore, now you see, now why, so now we are actually trying to utilize this fact. This is the important fact that we are going to utilize. If y is a subset of x and x is a small set, then y is a small set. And why? The proof is very simple. If this is small, we have just observed this is also small. That's the first part. Second, y is a subset of x implies y belongs to the power x. So these two tell us that small y. So utilizing this fact, therefore, it tells us and small y. So that was what I was writing as small xy implies. Right? Correct? Do you have the proof then? Yeah? Is it clear now?
Doctor, the proof for, okay, how then does it follow? Because that y is small given 1 and 2 there, because now what I think we can deduce, number 1 is
Okay. Okay.
But what is not
Yeah. There is a circularity in the
direct.
proof. So let me write down the proof completely. Yes, you're right. Because we are using this same idea while proving these facts also. You're right. So suppose, so first let's see how. So small x, so that is given. Okay. If I start from there, then my axiom of power set. So the proof will look like, let me start writing in this way. So if I start from small x, then there exists a z such that z is small and y is a subset of x implies y belongs to z. Right? This is axiom of power set. Axiom of power set, which is 5. Okay? Right?
It's axiom 4. It's axiom 4.
Axiom 4. Okay. Yeah, sorry. Small x gives me this. Okay. Now if so this is my axiom 4. So from here and this, sorry, the way of writing is not right. I was thinking whether we should start writing in this way. These are often called the Genzen trees, but I don't know. So you have small x and you have axiom 4. From there you can deduce that. So axiom 4 is already giving you that b. So from here you can deduce that 2 to the power x is a subset of b. Right? Why I say so? Why I go to 2 to the power x? So from this you can deduce that y belongs to b. Why? You are given this and you are given that y is a subset of x and you are given these 3 things. So axiom 4 is the one which is, we usually don't write axiom of 4 over here, we write axiom 4 over here. Well, this means that when I separate it by a blank, so this means one statement, then another statement, using my axiom 4, which axiom 4, you could even write it like this. Axiom 4 like this to say that b is given from axiom 4. So axiom 4, if you read it, that x is a small, for this x there exists a small set b such that whenever y is a subset of x it belongs. So you're given y is a subset of x, x is small, then you apply axiom 4 to get this, and this therefore tells you that small y. Yeah? So would you know? So this is the right thing, right? This is the exact proof, the complete formal proof. So what is it saying? If I take a small set and y subset of x, then axiom 4 gives me a small set b such that y is a member of b and hence y is a small set. Right? Clear?
Okay, yes.
Yeah. So by the way, these are often called Jensen trees. So these often are very formal presentation of a proof. So proofs actually look like this. So these are statements and we go up. So these are the up. So it's like an inverted tree. Yeah. So these branches are already all statements which have been proved or are actions, and then we get it. Okay. And in between them we often say that we often give the reason. And if we put a double line like this, it means it's to and fro. That means if we put a double line like this, it means that from the below you can come here, or from here you can come here. Okay. So that's another way of writing a proof. But usually what we will write is y is a subset of x. Y is a subset of x, and small x implies that there exists a b such that b is small and y belongs to b. So this is where we write the reason. So this is how you can follow any one of these routes. So this tells me that there exists a b such that y is in b, and this is the same thing as saying small y. Okay, so that gives me a complete proof of this statement. Clear? So now if we apply this, so applying this, all these three things are then consequences of this simple fact that if you have a small set, then it's any of its subset. In fact, that I gave as 53. Yeah, so you can use 53. So that proves the rest. So that is the first part of this first thing. So whatever I said so far is actually made a gist in 3.1.2, and then there's this exercise 3.1.2. I will keep that as open. Think about it. How can you make that equivalent? Okay, so what does it say? It says for all sets A and B, there exists a small set A, there's small set C, such that A is a subset of C and B is a subset of C. Okay? You can immediately see that there's some connection with this power set business and so on and so forth. And so if you so there's some kind of an interplay between power set and union and so on and so forth. So that's what this is about. Okay. Now 3.1.3 is just like giving giving an alternative definition of an ordered pair. Okay, so ordered pairs we defined as this. If x and y are small sets, this is defined as, so the moment I have x and y as small sets, then this is a small set and this is a small set. So the pair containing these two small sets is a small set. So this is a small set. Now, I think one of the exercises was that we proved this, that xy is equal to x prime y prime if and only if x is equal to x prime and y is equal to y prime. And this is the only intention of bringing in this ordered pair. So we want to give some kind of a relevance to the notion of a pair. Now I didn't say, so this notion of a successor of 0 of empty set, this is, if you remember, this is this. So that's why I said you assume this to empty set to be small. So this becomes exactly this. So this is usually denoted as a bold 1. Okay? A bold 2 is usually called the successor of 1. So what is that? This is 1 union this. So remember, if we allow, if we assume the empty set is a small set, that this is 1 is a small set, then union of 1, so 1 union this is a small set, and so 2 is a small set. So this is actually then nothing else but this. It is this and this, right? So if we write a bold 0 for the empty set, and this becomes this. Okay, 3 is the successor of 2, and this after calculation will come to this. Okay, so it is plain. So you know what we are trying to do, but we cannot state all of them. We do not have the power to do so now. We will see how we can see this idea of saying or putting this dot 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 is enough for us, but it is not possible. We understand that there is a pattern and we are getting hold of that pattern, but it is not possible for a machine to understand it. Okay, so when you are writing mathematics, it shouldn't be, so this is the hazy part, which this part is hazy. We need to pin it down. So we need an axiom for that. We'll see. That is the axiom of infinity that is going to come. Okay. So now, using this notion, Kuratowski gave an alternative definition, which is alternative definition of an ordered pair, which is you take 0 and the first. Okay. So you take this set and then you take 1 and the second one. Okay. And then you take this. Okay. So that was Kuratowski's definition of an ordered pair. Well, that also has this property. So that's the basic intent of this. Saying that, show that this same property holds with this definition. And so it just gives an idea that there can be several definitions of an ordered pair, but what are the main ingredients? The main ingredients are, for the notion of an ordered pair, first, if x and y are small, then the ordered pair, if I might write it in this way, the ordered pair of xy, so that is a set, is a small set. 2, ordered pair of xy, would be equal to the ordered pair of x prime y prime exactly when x is equal to x prime and y is equal to y prime. So these are the basic conditions that I need. And then there can be several definitions. This is one such. Krotowski is another such, and there are many others. I gave a link, you can read it. Okay. 3.4, 1.4 is, this is another way to, that's exactly our, yeah. So essentially what it says, it is trying to say that it's again reassuring our usual calculus, right? So the successor of a set is small, of a small set is small, and then if you have a large set, then there was a place where we did. 3.1.5 says that if you take the product, that means the usual things that we do, if you take two sets and take the set of all ordered pairs coming up from that, from those sets, then that is a small set. And that actually gives rise to the notion of a relation. And the next, obviously, is the calculus of relations. I hope you have gone through this section. This is more or less the rough outline. Now I want to listen from you. Your queries, doubts. Yeah. Yeah.
The exercise 3.1.4,
Mm.
number 55.
Yes.
We are saying that for all x, now for all x, we're not necessarily saying that x is small or x is large.
Yes. You're right. You're right. So that means I'm saying, so what is it saying? You have two sets. You have two sets A and B, right?
Yes.
Your axiom of extensionality and set building tells you that A and B are equal if and only if whatever they contain, right? Whatever they contain are same. So that means if x is contained in A, if and only if x is contained in B, right? That was essentially your axiom of extensionality and set building, right? Together it tells me this, right? In fact, it is only axiom of extensionality, but yes, there is a little bit of set building. But extensionality is essentially telling me this, right? It is telling me, it is defining equality in terms of belongs to, right?
Yes.
Equality, remember, equality of any two sets. They might be even large sets. They need not be small, right? So compare this with the axiom of extension. Extensionality, which is my axiom of 1, it says that, let me rewrite it as I did over there so that there is no misunderstanding. So it says that for all u, x belongs to u if and only if, sorry, the other way around. For all u, u belongs to x if and only if u belongs to y. This statement is equivalent to saying that x is equal to y. So it was defining equality in terms of belongs to. And here x and y need not be small. Yeah? But what is equation 55? That's another interesting thing. So just to keep this, I'm still writing it, rephrasing it just like this. So it is saying, for all u, x belongs to u if and only if, what is it? X belongs to u if and only if y belongs to u. So you see, I've just changed this. Right? Just x and u over here in this part has been interchanged, and over here y and u has been interchanged. I'm saying this still also says x is equal to y. But this is no more axiom, but this follows. So essentially, so let's look into 55 again. So it says, when you are saying for all u, x belongs to u if and only if y belongs to u, well, therefore you have automatically made this statement for only small sets x and y, right? Correct? So over here, x and y are both small.
Okay.
Now, so see, that's the difference. Over here in axiom of extensionality, there was no such extra thing. X and y can be anything. So here x and y are small. Otherwise, so now what it is saying, so if you give me two small sets, they are equal if and only if not only what they contain are same, they contain the same things, but in all sets in which they are contained are also same. So if x is contained in a set, then y must also be contained in that set. So contain and contained, as far as equality of small sets is concerned, are same thing. I mean to say, they must be, the list must be the same. So you see what is it saying? It is saying that two small sets are equal if and only if they contain the same elements, and if and only if they are contained in the same sets. So if they are not same, that means I will be able to find a set which contains x but doesn't contain y. That's the essential story behind this. If you give me any two unequal sets, I will be able to find a set which has x as a member but doesn't have y as a member, and the other way around. And a set which contains y as a member and doesn't contain x as a member. So do you see the other way of interpreting this? So this is actually kind of separating concerns. Means the moment you have two distinct sets, you can find a set which contains this. So you can somehow find a way to filter this out. So it contains this. It's very difficult to write it, so that's why I took a separate color. So this blue is a member of this red, but this one is not. So you see, you are having objects, they are all sets. When if you have two different objects, you can find out a set which contains one and doesn't contain the other. That's what it is saying. So this is the main story behind. It says that two distinct sets given if, so let me write it, if x and y are two distinct sets, then there exists a set U which has x as element, has x as one of its elements, and does not have y. And similarly, therefore, for the other one, there is a set V which has y as one of its elements and does not have x as one of its elements. So you get the repercussion, or what do you say, the consequence, or the crux of this. Yeah? Well, if we start thinking, if x and y are two sets, well, singleton x is obviously a set which contains x but doesn't contain y. It's as simple as this. Yes, it is true. Because x is a small set, then singleton x is one such. Yeah? So, you see, the idea is very simple, but to how do I say? To weed out that that extra inessential information. Given a set x, you are making the singleton x. Now, how do you make the singleton x? That is that set which comes from set building. It is the set Z such that Z is equal to x. So this set is actually singleton x. Okay. So this singleton x therefore contains x but doesn't contain y. Good. And all of this story is just crystallized in this way, that if x is not equal to y, then there exists a set U such that x is a member of U and y is not a member of U. And then if you rephrase this using our usual logical principles, 55 comes up. Yeah? So, that is, so you see how is it do you start seeing that a strange form is coming, a form is coming up from the raw syntax. These formulas are helping us to get hold of a form, of a strange structure, quite ghostly. Is it not? Something like those ghostly movies. Something fell, then some smoke starts coming out from that small dot, and then the small dot slowly gathers and gathers and gathers. That smoke gathers and gathers and gets into a form. right? It's something like that, smoky. It's still smoky, but it's still quite coming up, right? So you should start feeling that form coming up over here. Also, you see, these statements are saying if A and B are small sets, then Cartesian product is a small set. And then the moment we get this, we immediately can speak of a relation. A subset of a Cartesian. Well, what the hell is a subset of a Cartesian product? Given our intuitive understanding of sets, well, it is just a way of saying how certain elements of A are related to certain elements of B. Right? That's what is it. And that's this. So relations are nothing else but subsets of A cross B. So that's exactly what comes up. And then comes up this whole algebra. This whole algebra. Now, whenever I am writing this algebra, don't think that this is something which we know, and but try to read through the lines. It is saying a lot, and it is exactly giving a structure, that a form, a shape that is coming up slowly, and that's actually written in the remarks. With that, I will stop, and I'll ask you to say something now. I have spoken a lot. Yeah?
Okay, Doctor, you stopped, but then, for instance, I went through the notes.
Mm.
Problem 62 as well. I see that was that meant to be the intersection, or because now it looks like the logical operator, or and
You mean to say okay, the definition of a function, right?
yeah, the domain of yes.
Yeah. So let's see. So, what is our interpretation of a function? So it looks like this. We usually write it in this way. So if you have certain things, well, this will go, each such are called inputs of this. So this will go, each input will have a unique output. However, there can be two things which can go to the same output, right? And it's something like this. And some things might be open over here. So if this is the set A, and there is nothing left over, everything over here. So what is your idea? So for every element x of A, there exists a unique element y of B called the image of x. Yeah, this is how possibly most textbooks will define, right? So now that we know how to make our ordered pairs, so why don't we, so after this they will say that and y is the image of x under F. And this set will be made, again extensionality comes in and blah blah blah, and this will be called the graph of F. And there will be a few pictures, some functions, fx equal to x square and so on, and the graphs and blah blah blah, and why this is called the graphs will be shown. Now let's try and see what is the main intention behind this. So firstly, you are picking out a subset of A cross B, right? So the first thing is you are picking out a subset of A cross B. Now, what kind of subset? You must have for every element. So x belongs to A implies that there exists a y belongs to B such that the ordered pair xy is a member of F. Okay. Now you will say that there exists a unique such. So now you will say xy and xy prime belongs to F implies that y is equal to y prime. Agreed? So this is exactly this definition put down in a much more formal way. Correct?
Yes, the definition I've seen before, yes.
Others agree? Others?
Yes, doctor.
Okay. So now let's reformulate this again. So what we are saying, so reformulation I am putting it. So this one, we are saying that F is a relation. So yeah, F is a relation from A to B. Okay, I am going to say what is this and what is this. So what is, let's look into it. What is this? Look into the definition of what is the domain of this. Domain of F. It is a collection of all those x's for which there exists. It is exactly this formula. And domain of F is a subset of A. It doesn't say that it is all of A. What I am demanding is that the domain of F is exactly A. That's what I am saying. Being a relation doesn't tell me that the domain will be whole of A. It will be a subset of A. But I am demanding, forcing the equality. That's the second part. Now let me see this. Okay, xy belongs to F and xy prime belongs to F. Well, this is the same thing as saying that xy belongs to F and y prime x, because now I have defined my op relation f op. Okay. So this is this implies therefore that y prime y. So I am starting off with this. So this is F composed F of. Right? Clear? Yeah? So this is this part. This implies this. Now let me see the other way around. Y prime y belongs to F composed F. So this tells me that there exists a Z, let me, such that y prime z belongs to F and belongs to F of and zy belongs to F. Right? That's exactly the definition of F composed F of. Right? That's exactly the definition. 61. Right?
Yes, carry on.
Okay. So this is telling me that there exists a Z such that both Zy and Zy prime belongs to F. Alright? Yeah? Well, here your y and y prime is already there, so this part, so actually this is, so this statement, again as I said, is an implication statement, so essentially this part is therefore same as this, right? So this hypothesis is same as saying that, so the hypothesis part is same as saying y prime y is a member of F composed F of, right? This part is obviously same as saying y prime y is a member of delta of B, right? Where delta of B is what is delta of B? Well, delta of B is nothing else but XX, right? So this is exactly saying y prime y is in delta of B if and only if y is equal to y prime. So this C is therefore equivalent to saying F composed F of is a subset of delta. So a relation is a function if and only if its domain, a relation from A to B is a function if its domain is A, and F composed F of is a subset of the diagonal. So we started off by saying that relations are easier to describe in terms of this ordered pairs, and then we have defined a function as a special kind of relation. Well, that is exactly 2 and 3. The special kind of relation is what exactly 2 and 3 did. So this is what we have taken the definition of a relation of a function to be. Is that clear now? Yeah?
Yes.
So that's what so it is just rewriting this in this way. It is nothing new. In fact, what we will see is all these things. Well, I don't want to say so. I'll say what I was going to say. I'll stop. I'll wait for your inputs, queries, doubts, and blah blah blah. Answer them. Stop the class, and then I'll say something. Then I'll say something. So now I'm waiting for your inputs. Yeah? Anyone? Are you still alive?
I've got another question.
came as if from far, far away from the dreamland, it seems.
Sorry, speak up. I was just saying I have no questions. Although I don't know about the others.
Xander?
Hi, same doctor. I don't have any questions.
Malatse?
My question is not technical as such, but then more of will there be an advantage in seeing or introducing such new notation and things, or because of most of us, I think we are, for instance, accustomed to using the notation you used before on the left hand side while writing 1, 2, and 3, whereas now you introduce a slightly different notation there where we use partial with subscript 0 to denote the domain and such. Will there be an advantage as to using such notation?
Yeah, partial 0, if you don't like, you can change it to using like this. If you like, I have no problems with that. But okay. So that's a partial 0. You can, if you are not at all happy, and if you think it is going to collide with your partial derivative, you will replace it by domain OF. That should make it much more clearer, right? Yeah?
Okay.
But is that the only objection, or you wanted to say no, not about that only use of DOM, but you said that your main objection was that we are more accustomed with 1, 2, and 3. ABC is something which we... Have you seen it before? Anyone? Xander? I keep forgetting. Is it Xander or Ben who has a computer science background? Xander.
It's me, doctor.
Okay. Have you seen ABC?
No, doctor. It doesn't ring a bell.
Okay.
Could you maybe clarify?
No. Yeah. So now I formally close the class for today, but now I start saying something which I said I will say, so that you do not confuse. See, one has to understand that mathematics, firstly, as I said last time, you pick up an alphabet and you select and you alphabet. The moment you pick up the alphabet, then your logic will obviously I mean that you have already picked up your logic, and in our case it is the classical Boolean logic. So the moment you pick up your alphabet, you have picked up all the words. Done, immediate. All well-formed formulas. So alphabet and your initial predicate, list of predicates and operations, your words are immediately done. In those words, you still know which you call well-formed formulas. Some are statements which doesn't have any free variable. Now you start wondering. So you start giving truth values. You say, you assign some truth values. You say, well, these atomic Fermi statements are true, and so you say, these atomic statements are true and these atomic statements are false. The moment you do so, then all your statements immediately get the truth values. Okay? Immediately. Why? You know how to calculate the how you have obtained your statements. Phi, negation of phi, truth value will be the other one. Phi or psi, you know how to get phi and psi. Phi implies psi, yeah, blah blah blah, and so on. So you see, just by deciding on your alphabet and your predicates and operations and your basic set of atomic sentences or statements which are true, you have all of it. Do you really know? The question is, do you really know all the true statements? Essentially, yes, but given an arbitrary statement, you may not be able to say, it will take you some time, good time, to parse that statement down to the atomic ones, and then from there you rebuild your whether it is true or false. Well, that is a way out. Now, is there a better way? So then I come and suggest that, okay, why don't you consider some of those true atomic statements that you have given. Remember, atomic statements are very simple ones, right? They are their truth valuations are obviously, that evaluation is very simple. Now, I said, well, of those atomic statements which are true, why don't you identify some of them as your more basic ones and call them axioms? And why only some of them? Take some of these true statements to be axioms. So now I tell you another, I'm giving you another idea. You take some of these to be axioms, and then if you have a set of, from these axioms, you will be able to deduce, using modus ponens, other true statements, and you hope to get back. So you hope to get back all the true statements that your evaluation process has given by this process of deduction. And then our brother Gödel comes in and says, well, be careful. If your system is good enough, then there can be true statements which your axiom system will not be able to capture by your proof methods. Okay. So this is the complete syntactic side of the story. Okay. Now let's start looking into another side. As you are seeing now, we started off with certain strange statements, x belongs to y, and these axioms have already started giving us some kind of a structure, right? Obviously, we chose our statements, axiom of extensionality and blah, blah, blah. I gave lots of, I coaxed you to believe, and they should be true. And then some of the structure of our naive sets are coming up, right? You agree with that? This structure is giving us a form. Is giving us a form. And it is this form that is at the basis of theory building. The syntactic story, what I told you, yes, that is the real drumbeat. But hardly ever any mathematics comes up in that syntactic story. The first question is, which one of those, who is going to be that Puck who is going to tell me in my ears that take these few sentences and you will get a good result? God knows. So, I don't have that angel to tell me. So, what happens is, we usually have a structure, we usually have a form, and then try to find out a syntactic analog of it which kind of gives me this form. Now the idea of functions and relations have been there for ages. For ages. Even before Cantor, people knew the idea of a function. People knew the idea of a relation. They have spoken things about it. But not what did Cantor give us? Well, Cantor, as I said, gave us a very, very nice way to catch hold of these collections by names. So I can now hold them, and then he suggests the fact that I can hold them, then the whole Boolean algebra of propositions now turned out to be reframed. If you did that exercise before, you should have realized by now that this algebra of sets is nothing else but the Boolean algebra of propositions. That is what we are actually doing. Reframed in this form, okay, in this intersection, union, complementation, and so on and so forth. It is the same Boolean algebra that has been reframed. But it is giving a very nice structure, as you see. We can bring in all these bags, these pictures, intuitions, and so on. And then that bag intuition also gives us the notion of a function as we drew it over here, and also the notion of a relation, and everything goes well. But essentially it is this. So now the question that obviously comes up is, as Malatse asked, which one is the better one? Now, we will see later on, even speaking about elements elements are just some special functions. Okay, and given the notion of an element, we can define the notion of a relation and function. Now we have seen that if we are given the notion of a relation, we can speak about a function in either of these two ways, either 1, 2, 3 or ABC, whichever way you might. Now I am saying that if you give me a notion of an element, you can speak of relations and hence functions. But now I am giving you an extra bit. I am saying, if somehow you could idealize the properties of a function that we need, then we can speak about elements also. We don't need functions. We can speak about elements in terms of functions. So elements and functions become equally important. And indeed, this approach that I did take over here is another way to say that functions are nothing else but very special relations. So if you give me functions, also I can speak of relations. So not the root over here, but both these roots, that elements can be defined in terms of functions, as well as relations can be defined in terms of functions, are not very simple. They are a little more complicated. The latter one of getting relations via functions requires a little more over set theory, which is usually known as, it is actually a categorical idea. And well, the other one is also categorical, but it can still be phrased out here. So you see, the notion of element, the notion of function, the notion of relations, these are all very, the upshot of all this is, these are all very, very fundamental notions. and they are very much interconnected. So one can be defined in terms of the other, and you can as well define a perfectly valid theory, taking one of them as your starting point. We have, however, taken the notion of elementhood, which belongs to, as our starting point. We could have done the other way around. And there is a very, very, there is a Lavier-Chanuel approach to set theory, which actually takes this root of functions. It takes functions as much more elementary and starts saying things in terms of every other thing. And there is even later a root by just taking relations. And relations, once you start knowing relations, well, functions are very simple, but elements then come up even simpler. So you see, these are different approaches and different. So now the final bit of the story is this. So you somehow the idea looks like this, that there is this form, there is this structure there, already there in the world. You took one kind of syntax, okay? Lavier-Chanuel took another. Not this, say another color, say this. And there can be several others, I don't know. So essentially what we are trying to say is there can be several formal systems which kind of narrate the same structure or form or what we are trying to say. They can narrate the same thing. When you come now to the syntactic structure, then the question is, obviously, are they really the same? Or, well, there is a partly this says the same thing, and there are other facts which are said by, say, this blue kind of a syntactic development, but the red doesn't say it. So it becomes a newer structure then. So now you are trying to compare between two different syntactic structures. Yeah. So that comes up again at the next level. So you see, you have first a structure, you have first a syntactic theory. It is kind of giving you a structure, so the theory itself is giving you a form, a shape, and so on. And then you're trying to find whether this is the only way to say about it or there are others, and then how much and so on. So you see the latter one which I was saying, whenever you bring in another syntactic structure telling the same thing or more less thing and so on, it needs a bigger kind of a place to put them, right? So this hierarchy goes on and on and on. So it's a fascinating thing, but Malax's question, is this useful? Well, if they are equivalent, then if 1, 2, 3 is useful, then ABC is equally useful. That's one side. The other side, yes. Yes, because relations, for instance, relations are very well, relations and their compositions, their opposites, and blah blah blah, are very well modeled in database relational systems. It is exactly the relational algebra they use. And using database systems, the notion of a function or the notion of a key or an index node or an index column is essentially the notion of a function. And that can be uniquely, that immediately turns out to be an use in very large database systems. Just from relations you can pick up functions, and functions are exactly the indexing keys, right? So you see, it is used in several places. So yes, obviously if you prove equivalence, then if one is equivalent, the other important, the other is equally important. Okay, I will really stop here, and if you have anything to say, you can say. Have I pushed you into dreamlands or horror lands? Yeah?
What is the question, Doctor?
Yeah.
Yeah? Yes? You came broken, so I couldn't hear you.
Sorry. No, it's cool. I think, was the question regarding notation more than the concepts? Was it regarding the concepts?
Malatse?
The thing is, the concepts I do, okay, I think I do get them. So I was trying to understand whether adopting the new notation would be beneficial in the future. Because now, if now I have to start learning, for instance, a slightly different notation whereby it's not necessarily, or will not necessarily expand my understanding of the concepts, then I think for me it would not be fruitful to actually maybe start learning the notation.
You are very right. But
Only if okay.
But this new fact, we may not be using it directly in our computations anywhere. Okay? We will still be using that old thing that y is equal to fx and blah blah blah, all such things. Okay? But it now gives me an extra level of understanding, much more clarity in my understanding. So equivalent formulations are always good in that respect. It gives a clearer picture. It gives another facet of that same notion. So knowing equivalent descriptions is always good. It helps. It doesn't interfere with your exact calculations, as you are saying. You don't have to use it at all because it is equivalent. You can continue using your older, whatever you did before. But now you have an extra dimension, an extra. So could I address that question, right?
Fair enough.
So a function is a relation with the domain, is a relation from A to B with domain A, and precisely having this condition. That f composed, f op is the diagonal of is the diagonal. That delta is usually called the diagonal. So is the diagonal. So whenever you face such a thing in your calculation, you know that f is a function. Previously, you would have to sit down and put a little more, possibly 1 or 2 lines of work, but now you can just use it. Yeah?
Okay.
Okay. So if there are no further questions, then can we stop today? But as I said, Ben wants to talk for little more. If you want to stay back, I'll stop the recording then.